Probability is a measure of how likely an event is to occur from an experiment or an activity. In order for us to calculate a probability, we need to know how many ways the event can happen and how many possible outcomes exist for our activity. Let's take a look at an example. Let's say we're doing an experiment where we put slips of paper in a jar and we reach in and grab a slip of paper out. We want to ask questions like, how likely is it that I get a 7? Well, first we would need to know how many slips of paper are in the jar. So let's say that we have 1 through 19 in our jar. That's our sample space. We can describe our sample space as a picture with a rectangle, all of the sample space elements inside, or we can write it in set notation. We have curly brackets with all of our elements in the sample space listed out, separated by commas. Maybe we want to ask a question like, how likely is it that we get an even number when we pull a slip of paper out of this jar? Well, to do that, we would first define event A. That would be any even number as a result from this activity. I would need to look at how many even numbers are in my sample space, or how many even numbers are inside of that jar. So I can circle all of those even numbers and define that to be set A. We can list that in set notation as well. Maybe we want to talk about the probability that the result of this activity is a number greater than 13. Then we would define event B as the numbers greater than 13. In our visual, we could circle all of the numbers that are greater than 13, and we can write that in set notation as well. The visual that we're using is a Venn diagram, and we're going to go into that in a little bit more detail later on, but for now, notice that none of my sample space values duplicate. So although the numbers 14, 16, and 18 appear inside of set A as well as set B, I'm not writing those numbers twice. That's the point of using a Venn diagram where the two circles overlap. That tells us that those three numbers belong to both events. Now we're ready to calculate some probabilities. To find the probability that we reach into our jar and pull a slip of paper out and the number on the paper is an even number, we're looking at the probability that event A happens. Our notation for that is capital P, parentheses capital A. That says probability of event A happening. To determine that, we need to know how many ways could event A happen. Well, we could pick a 2, a 4, a 6, an 8, a 10, a 12, a 14, 16, or an 18. There are 9 ways that event A could happen. That's our numerator. The denominator is the number of outcomes in our sample space. We know our sample space is all of the whole numbers, 1 through 19, so there's 19 outcomes in our sample space. So how likely is it that event A happens? Well, it's 9 over 19, and we can convert that into a decimal or percent, but either way, this does represent a probability. Let's take a look at the probability that we reach into the jar and grab out a slip of paper with a number that's larger than 13 on it. That's the probability that event B happens. To find that probability, I need to count how many ways event B could happen. That would be my numerator. There's 6 different elements in event B, or there's 6 numbers that are greater than 13. That's my numerator, and again, my denominator is the size of my sample space, 19 elements. So to find a probability, you need to ask 2 things. 1, how many ways can the event that I'm considering occur? And 2, how big is my sample space? Those 2 answers would be your numerator and your denominator. Together, that fraction is your probability. Let's take a look at slightly more detailed events. What about A and B? In this case, the word and is saying both need to be true. So A and B means I'm only wanting to consider numbers that are inside of both circle A and circle B. That's the overlap here. So A and B is the three numbers 14, 16, and 18. When we say events A or B, that's like saying you can pick one or the other or both. So A or B is anything inside of circle A, as well as the elements that are inside of circle B. So both circles combined is the A or B. We have the even numbers 2 through 12, or rather 2 through 18, and then 15, 17, and 19. Now we have two new events that we can talk about. We can talk about A and B, which would be pulling out a slip of paper where the number on the paper is both even and greater than 13. We also talked about the event A or B, pulling out a slip of paper, the number on the paper is either even or it's a number greater than 13. So we have all of our evens and we have the numbers greater than 13. Now that we have those two events defined, we can talk about the probability that each of them happens. The probability that A and B happens, well, there's three ways for that event to happen. There's three elements in that set, and we're still looking at the same sample space, so our denominator is still 19. What about A or B? Counting how many elements belong to A or B, I see that there's 12. We have 12 possible ways to make the event A or B happen out of our entire sample space of 19. The next thing we're going to look at is the complement. Sometimes the complement is noted as a little apostrophe, so A apostrophe says A complement. Sometimes you'll see A complement as A with a little tiny superscript, letter C. Sometimes you'll see the complement written as A with a horizontal bar across the top of it. All three of these notations are exactly the same thing, the complement of A. Now when I say complement of A, I'm not saying, hey there A, you look pretty good today. What we mean by complement is if we took all of the elements of A and combined it with all of the complement elements, we would recreate the entire sample space. So we can see the elements that are inside of A, that's all the even numbers. The complement would be all of the odd numbers, the rest of the sample space. Notice that I'm completely ignoring event B here. When we're talking about the complement of A, we're only talking about A and the elements that are outside of A. Now we can talk about the probability that we pull a slip of paper out of our jar and the number is an odd number, meaning event A is happening. All we have to do is count how many elements belong to A complement. I count 10. We have 10 elements out of 19 in our sample space. Now I had mentioned that if you combined all of the elements from A with all of the complement elements, you would recreate the sample space. Another thing that's true is that if you take the probability of A and you add it to the probability of A complement, you will get a 100% chance or 19 out of 19 probability. So if I say, what are the odds that I pick an even number or an odd number? Well, those are the only choices we have, evens and odds. There's nothing in our sample space that isn't described by even or odd. Our last two probabilities are called conditional probabilities. Conditional probabilities can be a bit tricky, but visuals greatly help when talking about how to calculate these. So let's look at them one at a time. The probability that event A happens given the event B happens, that's written as P parentheses A, vertical line B. That vertical line is read as given. So A given B. Basically, that's saying what's the chances, the probability, that I pick an even number knowing that the number is greater than 13. So we're going to assume that B has definitely happened, meaning we're not going to let ourselves consider any of the numbers that exist outside of B. We're basically shrinking our sample space. We're not looking at all 19 numbers, we're looking at just the 6 numbers that are inside of B. So if we know our number belongs to event B, what's the probability that it also belongs to the group A? Well, there's 3 numbers that are in both A and B. So our conditional probability would say our new denominator, instead of 19, is the 6 numbers that are inside of event B. And our numerator, how many ways can A happen if we're only allowed to look inside of circle B? There's 3 possibilities. And that can actually be reduced. 3 over 6 is the same thing as 1/2, so we could say there's a 50-50 chance that if you look inside of circle B and pick a random number, that it's also a number that belongs to circle A. Now, something to pay close attention to is when we reverse these events in conditional probabilities, the outcomes are totally different. When it's A vertical bar B, that says only look inside of circle B, tell me how many ways A could happen. But if I say B vertical line A, that's saying the probability that an outcome matches event B given we're only looking inside of event A. So this time we're shrinking our sample space to match event A. We already said that there's 9 outcomes inside of event A. And of the 9 numbers inside of A, only 3 of them belong to the set B. So I would put 3 for my numerator. This is a fraction that reduces, so we can reduce 3 over 9 to be 1/3. Now, I told you that the order of the events in a conditional probability are important, and I want to drive that idea home. Are the probabilities equal, the 2 conditional probabilities that we just calculated? The answer is no. We know that A given B came out to 1/2, B given A came out to 1/3. Those are not the same number, so those probabilities are not equal.